So today we are going to build a stock price predictor model using recurrent neural networks. Now, for those who don't know what a recurrent neural network is, or RNN for short, it is a type of artificial intelligence designed to process sequences of data. It's a bit like a brain that remembers what it has seen before and uses that memory to understand what comes next in a sequence. So imagine that you're reading a book. As you read each word, you understand it based on the words that came before it, right? So your brain is forming connections between words to understand the meaning of the sentence as a whole or even a paragraph. And that is exactly kind of how a RNN works. Instead of words, however, RNNs often process things like time series data, so stock prices over time in our case, or even sequences of words in sentences. And each step in the sequence is like a word in a sentence. So the neural network takes in an input at each step and produces an output. And it remembers what it has seen before to help it understand the current input. Now, for our example, we are going to analyze stock prices from Roche. For those who are not in the know, Roche is a very beautiful Swiss biochemical company, and I definitely do not have any stocks invested in it. As you can see, I have already imported my libraries. We'll be using pandas, numpy, and yfinance. Yfinance in order to retrieve our stock data, and I have also downloaded both my train data and test data. For our train data, we'll be using stock prices going from the beginning of 2022 to the first day of 2024. As for our test data, we'll be using as a month worth of stock prices. So from January the 2nd to February the 1st. Now we can really take a look at our data, and this is what it looks like, although for our example we're just going to be using the open prices. So now we can go into our next step, and that's data pre-processing. Actually, let's do this. Okay, good. So we can already take a look at our data types stored within the data set. Train data.info. Okay, so as we can see, we don't have any null values, which is good, and the data type is exactly the way we want it. Okay, so first we're going to select our open prices, as I said, for our training features. So select open. And I'm going to use the method for shaping purposes. 1, 2. Okay. We can also take a look at the shapes of the train data and the train set. Okay, everything looks fine. Well, there's 6 columns and only 1 because we have only the open prices. So next, what we need to do is to scale our features. Now, I'm going to use the min-max scaling technique from the scikit-learn library. The min-max scaling technique is extremely helpful for scaling features to a specific range, typically between 0 and 1. And by doing this, we ensure that all features contribute equally to the analysis and prevent any particular feature from dominating, say, due to its scale, for example. So, feature scaling. We have to import a linear scale. Good. Next, we have to build our scalar. Okay. Well, what we have done here is quite simply, we have created an instance of our scalar, and since we want all of our values to be between 0 and 1, we simply have set the feature range to a tuple of 0 and 1, of course. And we can already apply our scaling transformation to the training set. So, train scale. That's fit. And conveniently, sklearn already gives us the fit transfer method. What this method does is it essentially computes the minimum and the maximum values of each feature in the training set, and then scales the features accordingly. So let's run it, and we can even take a look at how it's supposed to look like. Scaled. Perfect. As you can see, all of the values are between 0 and 1, exactly as we wanted. But, okay, so now we can already create our data structure. First, we have to create two empty lists. I'll show you why we have to make them. And we can also, what we're going to do now is, okay, so, what we're going to do now is we shall create a data structure with 60 time steps and one single output. The 60 is a bit of an arbitrary number, although this is the most convenient one for this case. And 505 is, if you remember here, our number of rows. So first we have to create the input sequences. Again, I'm going to write it down first and then explain. Okay. So these are our input sequences. What's going on over here is that for each iteration I, we are appending a subsequence of the scaled training set to X string. And this subsequence, of course, is going to span from I minus 60 to I, effectively creating a sequence of 60 time steps. Next, we have the output values, so Y string. Okay, good. Now in this case, for each iteration I, we are going to append the scale value at index I of the training set to Y string, and this of course corresponds to the next value immediately following the sequence of 60 time steps. But before we continue, we have to convert both of our lists into NumPy arrays. So, that being said, considering the model we are going to use, we have also to first reshape the data set. So next, the train. Wonderful. Okay, so we can actually build our model already. So building LSTM. Now, what's LSTM? What does it have to do with a recurrent neural network? Well, if you remember what I said at the beginning of this video, what a recurrent neural network does is that it processes and supposedly stores or remembers some of the data, of the information that it has previously seen. From a theoretical point of view, this should also work for long sequences, extended sequences of data, but unfortunately in practice that's not how it works. Pre-processed data or pre-processed information gets lost between one layer and the other. Luckily, the LSTM or long short-term memory system was invented, which essentially fixes this kind of problem. And so we can build our sequential model. Now, we have, I'm going to first build an empty model. So, oh, I forgot the S. Okay, good. And as I decided, this is essentially an empty model. It is an empty sequential model, meaning we can add our own layers by using the add method. So I'm going to build the first long short-term memory layer. Okay. I'm going to first write it down and then explain. Okay, so we have used the add method to add our first layer. The first parameter means that it has a total of 60 long short-term memory units. What this parameter does essentially, it determines the dimensionality of the output space. Then our activation function is the running function. We could test with others, but this one I believe is the most efficient one. Then we have set the return sequences to true, meaning it returns the full sequence of outputs for each input time step. Then input shape equals 60, 1. It simply expects input sequences of length 60 with one feature per time step. Next we need our dropout layer. The dropout layer for obvious reasons had to be added whenever we build whenever we add a layer. Okay, as you can see, there's nothing complicated. The reason why we add a dropout layer is mostly to prevent overfitting, and this 0.2 means that 20% of the neurons will be randomly set to 0 during what is the training, in order, of course, as I already said, to avoid overfitting. So we can already add our second layer. Can actually copy and paste this one. Although we have of course to remove the final parameter and keep anything else pretty much the same. Although for the other layers we are going to modify the number of the units. but this one will leave 60 as usual. And again, we add a dropout layer, always with a 0.2. Oops. Then we have our third layer, and for our third layer, we are actually going to increase our number of units and set it to 80. Up. 80, and then the fourth layer, and okay, in this case, since the fourth layer is also the last one in our case, we are going to increase the number of units to 120, and we can also remove the return sequences. Okay. Good, and then of course our dropout layer is always going to be 0.2. Good. And last but not least, we will of course need the output layer. Which is nothing more than model.add kr layers. We have to use dense units equals 1. Good. And it looks fine, so we can actually run and see. Oh, that didn't take too long. Now let's take a peek at our model summary. Okay, perfect. This is exactly what we want. So we have all of our layers. And we can proceed with the... Oh, I almost forgot we actually need to compile the model, otherwise we couldn't even use it. So model.compile, and as the optimizer we can use ADAM, and as our loss function we will simply use the mean squared error. I know they are not very original, but as long as they work, simple is better. Squared. Okay, now let's compile it. Okay, good. And now we can train our model. So, train the model. Model.fit, so our X string, Y string, batch size, let's go 32, and epochs 100. Now this might actually take a while, so I will just skip. Okay, so we are back. We have completed the training of our model, all 100 epochs. As we can see, our loss is really low, which is good. And we can already make predictions, which is great. So, going back to our original data, we have, okay, so we already have our test data, pretty good. First we have to get the real stock prices. So real stock prices. And and this is what we are going to use as to make our comparisons, of course. Then we have to get the predicted stock prices. First, I want to retrieve the total dataset. Total. Good. Now I want we want our inputs, which are going to be the stock prices of the previous 60 days for each day of January 2024. So inputs. Good. Then we have to reshape the inputs. And of course, we need to remember to scale our features. Okay, this is what it costs. Okay, so now we can finally create our test set. Okay, so what I have done until now, here we have done exactly what we had done earlier with our trained data set, but of course this time we're just going to do the same for the test data set. Then again we have to convert it into NumPy arrays, and finally convert it again the reshaping method that we had used earlier, which is of course required in order to process the data properly. Now we can also get to the predicted stock prices, which is exactly what we have been looking for until now. Okay. And remember that we also have to use the since we had used the reshape method earlier, we need to use the inverse transfer method this time. Okay, good. Now we can run it, and everything is working just fine. Now, all we have to do is take a look at how accurate our predictions have been so far. So, print predicted stock price. Let's go with the first values first, and print the real stock price. Okay, that's a bit too far off. Let's take a look, see a bit more into the data. Okay, 10. Okay, better. We're actually getting closer. Much better. Okay, so this is a rather unusual scenario where our earliest prediction actually quite far off from the mark, but the last one seems to actually get closer and closer to the real stock price. Since usually it is supposed to be the opposite. But again, this depends a lot on what kind of stock data we're using. Specifically, in this case we have used Roche, but perhaps something like, I don't know, Microsoft or Tesla would have yielded better results. It just means that the model we have used for Roche is not particularly suitable. Let me say that was all. I hope that this video has been useful, and I wish you a pleasant day.